Okay, so it's great that with maximum likelihood for this problem, the expected solution is the true solution. But even though the expected, in quotes, maximum likelihood solution is the correct one, should we actually expect to see something near that value? So one way to instantly understand this is if I have a Gaussian random variable with mean mu and sigma and variance sigma squared, and sigma squared is huge, then even though that random variable in expectation is equal to the mean, since the variance is so huge, I don't actually expect to see something close to the mean. I wouldn't be surprised if I saw a value, random value, very far away from the mean because the variance is so huge. So we've shown that the maximum likelihood solution is the correct one, but now we want to calculate the variance of that solution under the same modeling assumption. So to do this, we should also look at the covariance. So let's recall that if we have a vector y that's from a multivariate Gaussian with mean mu and covariance sigma, then the variance of that vector y, the covariance of that vector y, is equal to the expectation of the outer product of y with its mean subtracted off, and that's equal to the covariance matrix sigma. So this is the covariance, the way to calculate the covariance of the random vector y, and for the Gaussian, it's equal to sigma. And now plugging in the value mu for the expectation, we can equivalently write this in this way, where we show that the variance of y using this sequence where we actually take the outer product here, use the linearity of expectation to bring it to calculate these three separate expectations. We find that the expectation of y here is mu, and y transpose, the expectation of y transpose is mu transpose. So we have minus 2 mu times mu mu transpose plus mu mu transpose. So we have a minus mu mu transpose, and then the expectation of y y transpose. And that's equal to the variance. And so immediately we also can say that with this Gaussian, the expectation of y times y transpose is equal to the covariance plus the mean times the mean transpose. So this is an equality that we'll find useful in a moment. And so let's return to the least squares linear regression problem and calculate the covariance of the maximum likelihood solution under the Gaussian assumption. So again, to do this, what we're asking is the expectation of the maximum likelihood solution minus its expectation times that same thing transposed. Equivalently, what we're asking for is the expectation of the maximum likelihood solution times itself transpose, the expectation of this product, minus the expectation of the maximum likelihood solution times the transpose of that expectation. So this is from the previous slide where we have the expectation of y transpose, where the variance of this random vector is equal to the expectation of the outer product subtracted by the outer product of its mean. And so let's use this sequence of equalities to calculate this, which can be done in closed form. So we've already shown that this expectation, the maximum expectation of the maximum likelihood solution, is equal to the truth. Even though we don't know what it is, we can simply plug that value in there as a placeholder. So we know that whatever w is, the expectation of the maximum likelihood solution is equal to w. And then for the least squares solution here, or for the maximum likelihood solution here, actually plug it in. So this term here is equal to the maximum likelihood solution for w, and then this second term is equal to the transpose of that. And again, in this case, because these matrices involving x are constant, there's nothing random there, we can bring that outside of the expectation. And what we're really asking for is the expectation of y transpose. And now because y is a Gaussian with mean equal to x times w and covariance equal to sigma squared times I, From the previous slide, we know that this is equal to the covariance of this of y, which is sigma squared I, plus the outer product of the mean of the vector y, which is equal to x times w. So this is the mean, x times w, and then w transpose x transpose is the transpose of that mean. So we simply plug in, again, we're making this Gaussian assumption, so we can plug in these values here even though we don't actually know what w is. We assume that the vector w has this relationship to the output, and so we can plug this function in here and still work with it. We then simplify by separating these two terms out like this. So we multiply these two matrices on the outside by this, and then separately add that same multiplication with this term here. So here, this term is equal to this term, where we get rid of this, and then this term is the same thing except for we now focus on this part here. And then again, we keep the WW transpose like so. And now everything simplifies. So, for example, let's focus on this one here. We have x transpose x inverse times x transpose x. Whatever it turns out to be, this matrix product is equal to the identity matrix because they cancel each other out. And the same on this side. So this term is actually equal to W transpose, which will cancel that term. And then here, we have sigma squared times the identity. And since sigma squared is a scalar, we know that we can bring this term out front. And then we get a cancellation here. So x transpose times the identity is just x transpose. And so we get a cancellation of x transpose x times the inverse of that matrix product. So when we simplify these three terms, we actually find that the covariance of the maximum likelihood solution is equal to sigma squared times the inverse of x transpose x. Okay, so let's review again at a high level what is it that we've shown. So we've shown that if we make a Gaussian assumption, we assume that the vector of responses y is equal to the matrix of covariates or feature vectors x times the weight vector w plus independent Gaussian noise with this with variance sigma squared. So if we make this distribution assumption on the data that we observe, where again, notice that we've only defined a distribution on y, we haven't defined any distribution on x. And then we solve the least squares, or the maximum likelihood solution for w. They're the same solution. So we assume there's some true w. We don't observe it, but we do observe y, which is a random variable, a random vector according to this distribution. And then we try to do the inverse problem of learning what is w using maximum likelihood. Then the expected value of our maximum likelihood solution is equal to the truth. But the covariance of our maximum likelihood solution is equal to sigma squared times x transpose x inverse. So when using this probabilistic assumption, can we say that maximum likelihood or least squares is not going to work, or where we don't necessarily trust the maximum likelihood solution that we're going to get? So that's simply when the values in the covariance are very large. So this is a relative. The value, large versus small is all relative to the problem being considered. But if we want to be confident about our maximum likelihood vector w, when the values in this covariance are very, very large, we can't confidently say that our maximum likelihood solution is close to the truth. So let's look at a method that addresses this issue.